Hello there. In this video we're going to continue our investigation and exploration of the Euler Mascheroni constant. So recall this constant, which is typically represented by lowercase gamma, is defined to be equal to the limit as n approaches infinity of the nth harmonic number minus the natural log of n. So we've already talked about a couple characteristics, namely pretty much how we know this constant exists and what it's approximately equal to. So in this video we'll focus on how to get integral representations, namely 3 of them, for this particular constant. So to begin, let us first review just a couple identities that we have for the natural logarithm and the nth harmonic number. So recall the following identities. The nth harmonic number can be represented by the integral from 0 to 1 of 1 minus x to the n divided by 1 minus x dx. And you can easily prove this via factorization of the numerator. The second identity that you should be aware of is that the natural log of n can be represented by the integral from 0 to 1 of x to the m minus 1 divided by the natural log of x dx. And you can use Feynman's method to evaluate this result. So let's see if we can gather these two things together with its definition to generate a very simple integral representation for the Euler Mascheroni constant. So combining these two things, we have what? So gamma, which we know is the limit as n approaches infinity of the nth harmonic number minus the natural log of n, can be rewritten by replacing the nth harmonic number and the natural log of n with these two integral from 0 to 1 representations. So we can say that gamma is the same thing as writing the limit as n goes to infinity of the integral from 0 to 1 of 1 minus x to the n all over 1 minus x dx minus the integral from 0 to 1 of x to the m minus 1 all over the natural log of x dx. So both of these are integrals from 0 to 1, so I'm just going to factor out the integral and pull out my dx out of the right hand side. So I can rewrite this as gamma is equal to the limit as n goes to infinity of the integral from 0 to 1 of 1 minus x to the n minus 1 over x minus x to the m minus 1 all over the natural log of x dx. So one can verify that you can pass this limit underneath the integral sign because this is a integral of x, this is a limit of m, and this function underneath we can find that it is well behaved. So remember that x ranges from 0 to 1. So if x ranges from 0 to 1, then what can you say about the limit as n goes to infinity of x to the n and x to the n minus 1. So if x is a number between 0 and 1, when you exponentiate to a very large positive number, we can see that this limit is going to go to 0. So if that's the case, this is going to go to 0 and this is going to go to 0. So once you apply that limit, then we have gamma is equal to the integral from 0 to 1 of 1 over 1 minus x minus, so that negative and that negative is going to become a positive, so 1 over the natural log of x dx. So we can rewrite this a little bit more nicer as gamma is equal to the integral from 0 to 1 of 1 over 1 minus x plus 1 over the natural log of x dx. So this is the first integral representation for the Euler Mascheroni constant. So from this identity, we'll derive our second. So we're going to let, so we need to get rid of this natural logarithm on the bottom, so we can easily let x be equal to, say, e to the u. So if x is equal to e to the u, then dx is going to be equal to e to the u du. That's not very complicated. Let's look at our limits now. So when x is equal to 1 and when x is equal to 0, what does u become? So when x is equal to 1, we get 1 is equal to e to the u. So we see that u must be equal to 0. And when x is equal to 0, we have the equation u0 is equal to e to the u. And the only limiting value that can make that possible is negative infinity. So our limits from 0 to 1 become minus infinity to 0. So let's rewrite our integral in terms of that. So gamma is going to be equal to the integral from minus infinity to 0 of 1 over 1 minus x, so x is e to the u, plus 1 over, so natural log of x is going to be just u, so we can just write that as u, times dx, which is e to the u du. So let's distribute this e to the u into this expression. So we get that gamma is equal to the integral from minus infinity to 0 of e to the u all over 1 minus e to the u plus e to the u divided by u du. Now this integral from minus infinity to 0 typically isn't the more common integral. Usually we have integrals from 0 to infinity. So we can easily rewrite this. So we're going to let u be equal to minus x. So if u is minus x, du is going to be equal to minus dx. So no big deal there. So when u is equal to 0 and when u is equal to minus infinity, or as u goes to negative infinity, what do we have? So we have the equations 0 is equal to minus x and minus infinity is equal to minus x. So we get that x must go to 0 and x must go to positive infinity. So our limits from minus infinity to 0 is going to go from infinity to 0. So our integral, gamma, turns into infinity to 0 of, so we have e to the minus u all over 1 minus e to the u plus e to the minus u all over minus u, and du is going to be minus dx. So our minus sign can reverse our integral, and we can factor this minus sign into that plus. So we can rewrite this as gamma is equal to the integral from 0 to infinity of e to the minus u all over 1 minus e to the u minus e to the minus u all over u we should be in x form actually, right? Yes, all of these should be x's, x, and x. There we go. Yeah, sometimes we become friends with u's for so long that we forget exactly who our true friends are. There we go. Cool. So one last thing here, we have some negative exponentials here, so we can multiply top and bottom of these equations by e to the x, just to make things a little bit more nicer if you wish. So the e to the x times e to the minus x is going to go to 1. So we have the Euler Mascheroni constant is equal to the integral from 0 to infinity. So the top is going to be 1 all over e to the x minus 1. And then we have minus 1 over x e to the x dx. So this is the second common integral representation for Euler Mascheroni constant. So the third representation that we're going to derive is the integral from 0 to infinity of the natural log of x times e to the minus x dx, which is equivalently written as the integral from 0 to infinity of the natural log of x all over e to the x. We're going to prove that this is actually equal to the negative Euler Mascheroni constant. And this proof is a little bit more involved, but it's not too bad. So let's prove this. So we're going to recall something from basic limit calculus. So recall the limits as n goes to infinity of 1 minus x divided by n to the m is equal to e to the minus x. And that's very easy to verify via, say, L'Hopital's rule. So if that's the case, then we have our original integral, which I'm going to be focusing on in this form, is going to be equal to the limit as n goes to infinity. So we're going to rewrite the upper limit in terms of an arbitrary number that's going to go to infinity. So we can combine that into this same exact limit. So we can rewrite this as the limit n goes to infinity of 0 to m of the natural log of x times 1 minus x divided by n all raised to the n dx. Now we're going to set up for a power rule here. So we're going to decompose this 1 minus x over n to the n into two parts. namely 1 minus x over n to the m minus 1, and 1 minus x over m. Because when we integrate something to m minus 1, we're going to be adding 1 to that exponent and dividing by that new exponent. So it's easy to divide by n instead of, say, n plus 1, so we're going to decompose into this form. And it's very easy to see that as n goes to infinity, this term is going to go to 1 minus x over a really big number, as long as x is finite, is going to be equal to 1 minus 0, which is 1. So we can pretty much ignore that part and rewrite our integral star as the limit as n goes to infinity of the integral from 0 to m of the natural log of x times 1 minus x over n raised to the m minus 1 dx. So here I'm going to begin by using a substitution because I'm motivated to do some power rule. So I'm going to let u be equal to this interior expression. So when I multiply both sides by n, well, what is that going to give me? So that's going to give me nu is equal to n minus x. So that means x is going to be equal to n minus nu, or x is going to be equal to n times 1 minus u. So if that is the case, then what is dx going to be equal to? So dx is going to be equal to minus n du. And let's do some limits here as well. So when x is equal to 0 and when x is equal to n, what do we have for our values of u? So u is going to be equal to 1 minus 0 divided by n, so it's going to be equal to 1. And u for n is going to be equal to 1 minus n over n, so that's going to be 1 minus 1, which is going to be 0. So our limits from 0 to n is going to go to 1 to 0. So let's rewrite that integral. So our integral of interest is going to be equal to the limit as n goes to infinity of the integral from 1 to 0 of the natural log of, so we have x, which is now n times 1 minus u, and then we're going to have times our substitution u to the power n minus 1, and dx is in this case minus n times du. So I'm going to factor out this negative constant and also flip my integral, and keep in mind u is just a dummy variable, so I'm just going to switch back into x because I'm more comfortable with that. So we can rewrite this as star is equal to the limit as n goes to infinity of minus n times the integral, so no minus now, so n times the integral from 0 to 1 of the natural log of n times 1 minus u times u to the m minus 1 du. And we'll switch to x in the next step. So remember, the natural log of a times b can be separated as the natural log of a plus the natural log of b, where this is a and this is b. So we can also distribute this u to the m minus 1 over those two terms. So this is going to give us star is equal to the limit as n goes to infinity of n times the integral from 0 to 1 of the natural log of n times u to the m minus 1 plus the natural log of 1 minus u times u to the m minus 1 du. So notice that this natural log of n is independent of u, so we can factor that out outside of this integral. So we have star is going to be equal to the limit as n goes to infinity of n times the natural log of m times the integral from 0 to 1 of x to the m minus 1 dx, so I'm going to switch u to x here. And then plus, what do we have going on here? So we have n times the integral from 0 to 1 of the natural log of 1 minus x times x to the m minus 1 dx. So this integral right here is very straightforward, so we can use our power rule on that expression. So star is going to be equal to the limit, as n goes to infinity, of n times the natural log of n times, so when we increase the power by 1, we're going to get x to the n, so our new exponent is n, and we need to evaluate this as x goes to 1, subtract x goes to 0. And this last integral we'll deal with in just a moment. So that's n times the integral from 0 to 1 times the natural log of 1 minus x times x to the m minus 1 dx. So when we plug in x is equal to 1 into this expression, this is going to go to 1 divided by n. So we have 1 over n minus 0 over n, which is going to be 0. So we can pretty much ignore this portion. And we have n times 1 over n, which is just going to be 1. So we're just going to be left with a natural log of n in this first term. So we have star is equal to, the limit as n goes to infinity, of the natural log of n plus n times the integral from 0 to 1 of x to the n minus 1 times the natural log of 1 minus x dx. So this integral here that we're pretty much leaving, we have actually evaluated in the previous video, but if you want to prove this directly here, pretty much what you need to do is use the Taylor series for this expression and use some of your knowledge about harmonic numbers to pretty much simplify what that series is going to result in. And we proved that this integral is going to be equal to negative 1 over n times the nth harmonic number. So once we have that identity proven, so we have star is going to be equal to the limit as n goes to infinity of the natural log of n plus n times negative 1 divided by n times the nth harmonic number. So clearly, n times 1 over n is going to cancel, and we have that star is equal to the limit as n goes to infinity of the natural log of n minus the nth harmonic number. So what I'm going to do is I'm going to factor out a negative sign because this should look extremely familiar. So we have star is going to be equal to the negative limit as n goes to infinity of the nth harmonic number minus the natural log of n, and this should ring a bell. This is precisely the definition of the Euler Mascheroni constant. So therefore, star is going to be equal to minus gamma. In general, what we have proven is that the integral from 0 to infinity of the natural log of x times e to the minus x dx is equal to negative gamma. So that is one of the identities that we proved in this video. We proved a couple other representations for the Euler Mascheroni constant, namely the integral from 0 to 1 of 1 over 1 minus x plus 1 over the natural log of x dx is equal to positive gamma. And a third integral representation that we derived was the integral from 0 to infinity of 1 over e to the positive x minus 1 over x ex dx. And that is also equal to minus gamma. So we were able to prove these three integral representations for the Euler Mascheroni constant, which definitely have some connections to other functions, as we will see later.